Hey there, let's get right on into it. We're going to be talking about function operations today. You should have already looked at the Activate section of the course website, and that would have reviewed function notation. Now, function notation is what we are going to be using to specify operations on the output of a function. And what does that mean? Well, the operations we're going to start with are addition and subtraction, or sums and differences. We know that we can use function notation in two different ways. We can use it as f plus g of x, where we're having this f g inside the brackets, or a more probably familiar way for those who have already looked at the Activate section, f of x plus g of x. And subtraction, the exact same thing, f minus g of x, or f of x minus g of x. So let's start with an example. In example 6, and you can follow along on the course notes, Natalia was given h of x equals x squared minus 5x plus 4 and j of x equals x minus 4 and asked to find the value of j plus h of negative 2. And she used two different strategies as shown below. Now, the first thing it says is to annotate her work. And in this course, we're going to be talking about that a lot. We're going to be asked to really explain what's going on in words. And talking about math is important. And if we can say it in words, we're going to improve our learning. So for the first one here in blue, we have j plus h of negative 2 and j minus 2 plus h minus 2. Notice she just converted it. She's not using equal signs. We'll straighten that out later. J of negative 2 plus h of negative 2. Notice all she's done here is substituted in the value of negative 2 wherever there was an x in j of x minus 4. I'm going to grab a little pointer here. There we go. J of x minus 4, so she subbed in the 2 right here. And she did the same thing for the h of x. Notice she put it in brackets, always a wise decision, especially when we're subtracting this when we have addition. So that doesn't affect us so much. But let's go ahead. Negative 2, well, that breaks out to be negative 2 right here. Negative 2 squared, positive 4. Negative 2 times negative 2, positive 10. And we get the final answer of 12. Now, in the other example over here, notice what she did. Rather than substitute in the negative 2 first, she actually wrote down the equation for x minus 4 and the other one here for h of x, x squared minus 5x plus 4. She simplified the formula. So the x squared, there was no other like term that came out in front. The negative 4 and the positive 4 canceled. And then we had the x plus a negative 5, or in other words, x minus 5 to get the negative 4x. After she's done this, she went ahead and then did the substitution. Doing the math ends up with the same answer, and that's exactly what we're hoping for. Let's go back. And it says, which strategy do you prefer? And when might that be more efficient, less efficient? I find this one at the start looks quicker. We just sub in the negative 2, find the answer, done. However, this one here, once we got to this point here, then it was quicker. So if we had to actually solve for more than one value of x, maybe they gave us 2 or 3 to solve for, well, once we got this done, then we would only have to repeat this little process 2 more times, rather than going through this process 3 times. So something to keep in mind. So f of 2 plus g of 3. And what do we get here? Well, f of 2, we said we're going to use this example. We just made it up, but that's okay. That is 2 plus 2 plus g of 3. Well, that would be 3 squared. Now, putting all that in together, 2 plus 2 is 4 plus 9. And here we get 4 plus 9. That equals 13. Well, what happens when we say f plus g of 5? And this should actually have brackets around it like that. Well, let's look at that one. That really is the same thing. I mean, we could do it. Let's go back and let's do it this way. Just to practice, we're going to say f of x is x plus 2 plus g of x is that. Now let's write that in descending order. Remember, anytime you can stop and pause the video just to slow it down a little bit and get some notes taken down. Well, here we have this. So if we wanted to say f plus g of 5, we're going to substitute our 5 in here. And you already might see that this is definitely not going to equal 13 with that 5 squared there. That gives us 25 plus 5 plus 2, which gives us 32. And therefore, you can see that this does not equal that. Well, the reason that is that f plus g of 5 equals f of 5 plus g of 5. Notice the x is actually the same, and when we write this function notation like this must be the same x right here. So we can't split it apart into two numbers that add together to make x. Let's keep going. Okay, now here it says that we have, let's turn this off. The function f of x, g of x, h of x, and j of x are shown to the right. Now remember, functions can occur in many different forms. We often think of them as equations, but they can be like f of x and g of x, which are a set of ordered pairs. They can be in mapping notation, like this h of x, or they can be as a table of values, like j of x. So let's go over here, and we're going to determine j minus g of 1. Well, j minus g of 1 is the same thing as saying j of 1 minus g of 1. So we have to determine j of 1 when it equals 1. And we go over to our table of values, find where x equals 1, because that's the input. And we're going to get the output of 4, and we got that right there. And then we have the g of 1. Well, the g of 1 up there is an ordered pair. Remember, ordered pairs represent the input x and the output y. So when we put in 1, we get out 5. So putting all of that together, we get 4 minus 5, or negative 1. Let's keep going to the next part of this question. Here we're asked to determine the value of f of 3 and h of 3. Same idea. F of 3 is that ordered pair up there. So we get 3 going in, 5 coming out. And then the h of 3, well, look what happened here. A common mistake for students is that they try to extend these mapping notations or tables. The thing is with these is that these represent the function as is, and we can't extend beyond it. If we do not have a value in x, or in other words, that domain, then that value does not exist. So when we put this together, we say that this is undefined because it is not defined in the domain of x. In this particular example, the domain are these 5 numbers alone, and that's it. So we can state that when one of the functions is undefined for the given value of x, or not in the domain, the solution of the function operation is also undefined. Let's try another one. It's asking, what will you write when there is no answer? What work will you show? So when we have something that's undefined, what are we going to say? Well, when there is no answer, you will want to say that the expression is undefined. And we want to state that the value of x is not in the domain of the given function, or maybe functions. Now let's pause the video. Now that you've gotten a few examples under your belt, let's try some of these. In the practice of the section of this lesson, try questions 1, 3, and 4. Pause the video, give them a go. If you're not getting the answers at the bottom, make sure you're contacting your teacher for help. Welcome back. I hope those questions didn't give you too much trouble. So let's move into example 9. Use the functions f of x equals the square root of x and g of x equals x minus 2 to determine the values of the following expressions if possible. Ooh, foreshadowing. Let's see what we get here. Well, if we want to find f plus g of negative 1, we can actually just go f of negative 1 plus g of negative 1. I like writing it in this version first. I just find it's easier to look at. And let's go put that into the square root of -1. And then we're going to put the -1 into, I'm going to put brackets in here. Good idea to get into that habit. Helps you deal with negatives later on. And then we get, well, what is the square root of -1, I wonder? Oh, yeah, it's undefined. You can't take the square root of a negative number. Even though this one is -3, it doesn't even matter anymore because as soon as this happens to be undefined, remember the whole thing is undefined. And if we want to be using some shorthand, a lot of students I see use UD. Let's try the next one. G of 1 equals f of 2. Well, it's already in my favorite way, so I'm just going to go 1 minus 2, and I'm going to subtract square root of 2. Now, everything here is solid. That 2, it's okay to say the square root of 2. That equals 1 minus 2 is -1 minus root 2. Now, this is an exact value. In Math 30-1, I would really like to see students leave final answers as exact values unless they tell you to round to the nearest 10th, 100th, etc. Otherwise, we're going to focus on leaving things like this. Let's move on to the next question. Okay, let's look at example 10. All the good stuff is starting to happen now. We're starting to look at the graphs. The functions f of x and g of x are shown on the graph below here. Determine the values of f of 2 plus g of 2. Well, remember, the 2 is the input, and we need to figure out an output. And the output is the y value associated with when x equals 2. Now for f of 2, look right there. We have that dot on the x equals 2. Well, what is the y value of that? Because that's already touching the f of x graph, the blue graph. Well, the y of that is 0. Well, what about the g of x? Well, if we go up to the green graph, the g of x graph, and then go over to get the output value of the g of x, which is now 2, we can now say that f of 2 plus g of 2 equals 0 plus 2. Or in other words, when we add those two values together, we get 2. So f plus g of 2 is 2. Now we're going to do it again, but this time with subtraction or finding the difference between f and g at -1. Okay, let's do it. Well, -1 for the f of x, we're going to go up till it gets to the line, go over to y, and that's at 3. But when we do it for the g, we get it here at 1. So in other words, we can say 3 plus 1 with 4. So notice we got different values than last time, of course. We're using different numbers. Now, the function of f of x and g of x are shown on the graph. Write two expressions using function notation and the operation of addition and subtraction that have no answer. Pause the video and see what you come up with. Well, let's look what you came up with. First of all, you might have noticed that after x equals -2, g of x is undefined, and that makes sense for radicals. We always know in radicals that there are parts of those graphs that do not exist. And so anything we chose here in this part, in other words, that is not in the domain of g of x, will result in an operation of functions that is undefined. For instance, we could have said f of -4 plus g of -4. That wouldn't exist because g of -4 doesn't exist. We could also say f minus g of -3. Any one of that number that you picked to the left of -2 is going to work. If you want me to check your answer, make sure you just send me an email. Let's move on to some more graphing. In example 11 here, it says the partial graphs of f of x and g of x respectively are shown below. Do you expect the graph of f minus g of x to be more linear or more quadratic? So what we're doing, we're going to subtract away g of x from this one. What do you think is going to happen? We're subtracting a linear graph away from a quadratic one. And notice For instance, here, this graph is increasing left of 0, and here, this graph is increasing. Now on this side, this one is getting smaller as we get away from 0, the y-axis, but this one's getting bigger. So if we're subtracting things, think about how that might affect the graph and see if you can get a picture in your mind even before we do the work. Let's keep moving. So now we're going to draw the graphs of f minus g of x. When we do this, now we could go ahead and figure out the formula, the equation for the function that's the quadratic and the linear function, but we may not have that option all the time. So the method I'm giving you today is using table of values first, in case we come across graphs that we can't use equations or determine the equations up front. So the first thing I want to do to create tables of values is I want to pick some points. I like to pick the small points. I like to pick small numbers. So what I do, I start with numbers generally between negative and 5 if possible. I want to pick points that are on crosshairs. And what I mean by that are where those grid lines cross over. So notice these points I picked here are definitely on the crosshairs. That means they're just going to be integer values and easier to work with. Sometimes that's not possible, but right now this is what we're doing. And I do the same for the g of x. Notice here I picked -3, -2, 0, 2, and 3 for x values of these ordered pairs. I'm going to pick the same x values on the g of x. Well, why do I want to do that? Because I'm going to be creating a table of values. So I take those ordered pairs and I put them into a chart. When x equals -3, -2, we got f of x equals 5, sorry. When x equals -2, we got 0, -4, 0, and 5. So now we have this nice table of values. And we could do this even if we didn't know the equation of the graph. Now what about the line? Same thing. We just find out the output values or the g of x values. -1, 0, 2, 4, and 5. So now we have two table of values. So what are we going to do with these? We're going to subtract them. So now what we're going to do is create a third table of values where we're subtracting the outputs of the other two, the functions that were separate. So here, notice let me get my pointer out for this one. Here we had 5 and -1. Well, 5, it's all drawing the graph and everything. Spoiler alert, okay. 5 minus 1. Well, 5 minus a -1 is a +6. 0 minus 0, well, still 0. -4 minus 2 is -6. And we continue down the line until we get these. Now, if you want to check them, again, remember, pause the video and check them out. Notice the columns of all of these table values are the same because we're looking at when is the input, for instance, in the first row, -3, the second row, -2, 0, 2, and 3 down the line. Well, I've already spoiled the surprise. So what we have going on here is I have taken this and I have put in those ordered pairs. Now, the thing is with this, sometimes we might miss some important points. For instance, in this one, notice here, I didn't pick when x equaled 1 right here. Which means I might miss some kind of key points. And I understand that may happen, and I'm pretty lenient with that. There are situations where when you do this, you should be able to recognize these points here. But in this particular case, it would have been pretty difficult to figure this one out. So that's okay. We're in for the process right here. So let's turn off the laser pointer and let's keep moving. Now, with keeping in mind this original graphs that we had, remember that one of them looked like was a quadratic, the other one was linear. And it's asking now, will this new function have a domain restriction? Now, thinking back, some of our other operations on functions did have domain restrictions. For instance, that example previously that looked like a radical function, it did not exist on certain parts of the graph, the chord order on the Cartesian plane. But our quadratics in the domain, well, the domain for a quadratic is the real numbers. Same for a linear. Linear functions also have domains with no restrictions. So if we're combining two functions that have no restrictions, then our combined function will also have no restrictions. So in this one right here, since neither function has a restriction on the domain, in other words, x is an element of the real numbers, then neither will f minus g. Now the last one here, it says given f of x equals x squared minus 4, and g of x equals x plus 2, write a simplified equation for f minus g of x. And does this equation support your answer above, meaning when we graphed it for b? So let's look at that. Well, when we put f minus g of x together, we get x squared minus 4 minus g plus 2. And we get x squared minus 4 minus x minus 2. Notice what happened there. That negative had to be distributed through the x and the negative 2. So we're subtracting the positive. So notice it becomes minus 2. Pulling all the like terms together, we get x squared minus x minus 6. Now I want you to check it out for me. I want you to go and grab your graphing calculator and put that in the y equals and see what you get. Okay, so you may have noticed that when you put it in your calculator, it looked really close to the graph that we got earlier. So you know that you're on the right track when that happened. Good work. Let's keep going. Slow motion. Okay, example 12. The partial graphs of h of x and g of x respectively are shown below. Now we're asked to graph h of g of x. Can we do it? You bet we can. We're going to do a table of values one more time. Let's get it together and see what we come up with. Well, let's grab our points. We're going to choose when x equals -4, -2, 0, 2, and 4 on the positive side. Now notice on this one right here, I didn't mention it in the parabola one, the quadratic one, but I'm going to mention it here. When we pick points for things that turn, for instance, like a quadratic goes up and down or down and up, same with absolutes, they go down and then up. We're going to want to make sure that we're picking the x value associated with any points or turns on the graph. So we're going to pick x equals 0 here for sure. So we're going to pick those points here. And we're going to get our table of values. Now, how about you pause the video, fill in this table of values yourself, come back, and we're going to put it all together and see how you did. Well, welcome back. Let's see how this went for you. Well, this is what I got. When x equals -4, I got these values. Look what we got here. We got a bunch of zeros, 4 and then an 8. And I wonder why that is. Let's think about that. Notice here, when x equals -4, this was -3, +3, -1, +1. In other words, anything to the left of the 0 canceled out the line to the right of the 0. Let's look at that when we put it on a graph and graph it. Well, we have this lovely table of values now. All we have to do is graph these ordered pairs. We put those on, and we extend with lines going off the graph to indicate that it's going off to positive and negative infinity. And notice here, we have this horizontal line on the x-axis, which makes sense because all of these values here are 0, meaning they lie on the x-axis. Now in this question, it's asking the partial graphs of h of x. Will this new function have a domain restriction? Again, in this question, no, there's no restrictions on the domain of the original function h of x or j of x. So this difference of function will also not have any restrictions on the domain. So pause the video again, break out the practice work, and see if you can tackle questions 2 and 5. And then when you're finished, head on back and we're going to head into the last few questions here. Well, welcome back. We can't get enough of graphing. So let's go ahead and we're going to draw the graphs of each of these functions. Boom, I've already done it. So all I've done is I put these graphs f of x, which is the square root of x, and g of x, which is the linear graph x minus 2, and put them here together like that. Now we're going to be asked to write the domain of each of these functions. So we've done a couple where we've put things together and then then kind of considered the domain. But let's look at the graph and then consider the domain right away. In f of x, we can easily see that for that one, it does not exist to the left of 0. In other words, f of x must be greater or equal to 0, which makes sense for this radical function right here. Now, the g of x, well, g of x also does not have any restrictions on the domain. It goes off to positive and negative infinity, in other words, the real numbers. Now, when it comes to the range of f of x, because we have this endpoint here, that means there is a restriction on the range, and range is when y is greater than equal to 0. But over here on the g of x, no restriction, so y is the real numbers. Now, if we put that in interval notation, remember for interval notation, square brackets mean that the number is included, and round brackets mean that the number is not included. However, in the case of negative and positive infinity, we include round brackets. We never put a square bracket on infinity because infinity technically is not a number, it's a concept. So we just put that round bracket there on the infinity. So for f of x, the domain is 0 to infinity, and g of x from negative infinity to positive infinity. And in set notation for the domain, we would put that one here. F of x equals x. Sorry, f of x has a domain of x such that, that's what the line means, 0 is less than or equal to x, where x is an element of the real numbers. And for g of x, x is an element of the real numbers. Now I noticed that we didn't put our range in here, so let's go and put that. For the range, now the range is not going to look too much different here. We could actually say this is also the domain and range notation right here. However, in this notation, the set notation, we would need to change this to y. So for this, we would say 0 less than or equal to y, where y is an element of the real numbers. And then we would do that. That would signify it is actually a range and not a domain. And then down here for the range, we would say y is an element of the real numbers. There we go. Let's keep going. All right. So now we're down to drawing the graph of this thing. Well, when we draw this kind of graph, first thing we want to do, let's go ahead and make an equation. Now we've been making tables of values before, but we can go ahead and go g of x minus f of x and just plug in those formulas. It doesn't matter if it kind of looks strange over here. We're just going to go ahead and do it anyways. So when we put it into our calculator in one of the y equals button of our calculator, making sure our window settings are right, we see this little thing like here. Now, this one's a little tricky. This part here on the graph, when you're looking on the calculator, is a little difficult to see, not going to lie. Even if you kind of shorten up the window setting to -5 to 5, I still kind of find that it's hard to see that it's actually dipping. Okay, so when you draw these, a way to kind of make that stand out is to trace it. And I'm going to show you that in a little moment, how we can make it easier to see. Now, the reason we want to find that little dip is going to actually come into play in a moment. In the domain of this, however, the domain is where the x values exist. Well, in this particular one, everything exists to the right of the 0, x equal to 0, and it actually includes 0. So when we write this in interval notation or set notation, we would write them like this. Now, explain why the new function has a limited domain. Well, in this case, remember, f of x equals the square root of x and g of x equals x minus 2, well, that root x there, that has a limit on its domain. And so since the domain of f of x is restricted to values greater than or equal to 0, the domain of k of x is also restricted to values of x that are greater or equal to 0. It says it's E, but it's F. It says, use technology to graph k of x and determine the range in set or interval notation. Just give me a second here. Let me grab my calculator. Okay, so if I put this in here, I've already gone ahead and put my value in here and I've graphed it. Remember what I was saying? It's hard to see that this is actually kind of dipping down. Just to make sure that you're not making kind of any errors there. Oops, I'm going all over the place here. Let's just graph that. If we trace that and start, notice here, I can't go any further than 0. It won't let me. So if I start going to the right, you're noticing there, oh, see how it dropped down? And now it's starting to go back up. That tells you there's a little bit of a minimum there. And that's important when it comes to the range. We might want to go and say, oh, well, when my y-intercept is my minimum point. So I would go 1 when x equals 0. I'm going to find my y-intercept. And so I would think the range is -2, y is greater than or equal to -2. But that's not the case, because notice as we kind of do that trace thing again and slip down, oh, it's going a little bit below. So what we're going to do is use the minimum function on the calculator and go second trace and go 3 for minimum. We're going to make sure we're to the left. It always asks you to guess. Is that it? Yeah, it is. And then to the right. Yeah, let's go to the right. Now it's asking, can we guess? Yeah, of course. And notice these 2 arrows at the top here. That just tells you it's looking between those 2. And you hit enter and you wait and you find that the y value, the most minimum y value is -2.25. So when you put that together, we can say it in interval notation, or we can say it in set notation. Well, let's keep going. So let's put it all together. Restrictions on combined functions. The domain of y equals f plus or minus g of x will be the set of all values common to the domain for y equals f of x and y equals g of x. And the range of f plus or minus g of x can be determined using graphing technology, just like we did. So combined functions will have a domain restriction when one or both of the original functions has a domain restriction. And we've already looked at a couple of examples like that, but let's keep going. I want you to pause the video, give these a try, and see, oops, let's go back. Give these a try, and if you have any questions, remember, you're always welcome to get in touch. Okay, example 4. We're going to look at a little bit of strategy here to kind of give us a visual on how we can combine these domains of functions, and so that we could see it quite easy. So in the domain of f of x, where x is greater than or equal to -6, and the domain of g of x, where x is less than 4, and x is an element of the real numbers, a student created a drawing below to determine the domain of f minus g of x. And the first part of this question is, again, that annotate. Let's explain what's going on. Well, for x greater than or equal to -6, the student drew a line, put in -5 and 5, and kind of guesstimated where this -6 is. So it's a sketch. We'll give them a bit of a break that it's not to scale. They put a dot and they drew a red line going to the right. And that would mean, well, x greater than, because everything greater is to the right. And then for the domain of g of x, that would be the green line. It says x less than 4. Notice there's a little open dot here, and drew the green line over there. Perfect. We got that. So then it's saying, how could the student use the drawing to determine the domain of f minus g of x? Well, we want to find the overlap of these 2 domains. Well, on this end, because of that solid dot and that green is under it, we can say the minimum value on the domain is going to be -6. However, heading over here, we have this open dot at 4. So that's going to tell us that we can't be greater than 4 or we can't equal 4. Remember, open dot means up to but not equal to 4. So in other words, we have this upper end of the domain, and we're going to go ahead and write it in set notation where x is such that -6 is less than or equal to x is less than to 4. Notice here, I'm putting my minimum value here, my maximum value here. And that's a great habit to get into. Put the minimum value to the right, the maximum value to the left. And that way you won't get these signs mixed up. Sometimes that happens a little bit. Okay, let's keep going. Example 15. Angela said that h of x is x squared minus 5x plus 4 could be written as the sum of two functions, f of x equals x squared minus 10 of x, and g of x equals 5x plus 4. And let's see if that makes sense. Well, if we have h of x equals x, or let's put that back a bit, equals f of x plus g of x, and f of x equals x squared minus 10x, and then we're going to add our g of x, which is 5x plus 4. All we're going to do is gather those like terms, and we get x squared minus 5x plus 4, and sure enough, those two equal each other. But they're asking us to figure out a couple other functions that we could add together, or that would create h of x equal to that. So let's give that a try. Well, there are an infinite possibility of answers here. I like to go for the simple one. I'm just going to say f of x is x squared minus 5x and g of x is 4, so that when I add them together, it works. I can also say when f of x equals x squared and g of x equals minus 5x plus 4, go for the easy. It doesn't have to be complicated. Now, we could get a little more complicated, something like this. Notice here, the difference between the 2x squared and the minus x squared term would give us that x squared term of h of x. 3x minus 8x is minus 5x, and negative 2 plus 6 is a positive 4. So that would give us the same value. But again, I'm not looking for complex. I'm looking for two values that add together to make the same h of x. And here we go. You might have come up with something different. And remember, you can always show your teacher and see if your answer works as well. Okay. Use the reciprocal functions below to answer the following questions that follow. This is a bigger question. Let's look at it. Well, remember, reciprocal functions are 1 over something. In this case, it looks like we have a couple quadratics in the denominator. And remember, for reciprocal functions, that the denominator cannot equal to 0. So that's going to affect the domains of these functions. So what we're going to do is we are going to solve the denominator for when it equals 0. So the first thing I do, I write down the denominator equals to 0, and I factor. So we got to break out our factoring skills. And if you need a little help with that, I'll be putting some factoring tutorials on a tutorial page of the website. X squared minus 15x plus 50 equals 0. So we have x minus 10 and x minus 5 equals 0, which means x cannot equal 10 and x cannot equal 5. Let's head on over to the other one. Well, that one, its denominator is equal to 0, and we're going to factor that out. That one's easy peasy. Just take out a value of x. And that means x cannot equal 0. Don't forget the 0 for that x term, but x cannot equal to 10. So now combined here, we have three different values that x cannot equal. Well, why is that important? Well, what if we were determining a simplified equation for this? Well, let's go ahead and do that. To find this, we're going to go ahead and we're going to go and just, I like to write things out. Equals, so it's going to be f of x, so I'm going to go 1 over x minus 10 times x minus 5. And then I'm going to subtract 1 over, I'm starting to go on a little angle here, x over x minus 10. When I put these together, what I'm going to do is I'm going to find a common denominator. Well, I look at my factors. This factor is here, so I'm going to add that to my common denominator. This factor is here. I'm going to add that one. And then I have this factor here is x. So this is going to be my new common denominator. So what are we going to do here? Well, we're going to multiply numerator and denominator by anything that's missing. What does that mean? Well, that means for this term, I'm going to multiply top and bottom by x because it doesn't have that x term. And then for this one right here, I'm going to multiply top and bottom by x minus 5. I'm putting it in the brackets because we don't want to mess it up. So this is what I have right here. And the reason I put it in the brackets is for the next step. I want to remind myself that I am subtracting everything in there, which means it also will subtract not only the x, but the negative 5. And when we subtract a negative, it's like adding the positive. So that means when I do that, I'm going to go x minus x plus 5. These cancel out, but don't forget, this is over here like this. And if you want to make it nice and pretty, it's just going to be x over x times x minus 10 times x minus 5. I want you to notice that I am stacking my equal signs as I go down. I am not working across this way or using arrows for my equal signs. I want to really kind of get everybody into the habit of showing their math correctly. Now, one thing we have to keep in mind here, because this is a combined function, and I'm just going to erase this right now. We're going to move ahead here. Is those individual restrictions we found in part A are going to affect the restrictions of the difference of these two functions. So remember, we had this function right here, but at the beginning, we found that these were the restrictions. So in other words, the restrictions on f minus g of x is the combination of the restrictions of f of x and g of x. And notice it even carried through to the, oops, let's go back. It even carried through in that now the denominator also has all these restrictions. Keep in mind, however, sometimes the final answer here may lose, and we're going to talk about this later on, but just keep in mind, we might lose a factor in our simplification, which means we still have to consider the values at the beginning. Okay, hold that, put it in your back pocket. Let's keep going. Now, we're going to be looking at some pretty common graphs. These are all graphs you've seen in 10C and 20-1. Now, on your paper, just below, you're going to see 6 functions in function notation, and those are the ones they're referring to. I want you to pause the video and see if you can match them to these graphs. Welcome back. Nice to have you back. Let's look at what we got here. Okay, well, linear is going to be that f of x function. The quadratic is the g of x function. Cubic is the h of x. Rational is m of x. Absolute value function k of x. And the radical is the square root of x, and it looks like our square root of x had an accident. I hope you got the driver's license plate. Well, the next part of this is the domains. Well, we're pretty familiar with all these domains. Quite a few of these we've talked about already. Domains of linears are real, as are quadratics and cubics. Rationals, remember rationals can't cross the line where x equals 0 because it's in the denominator and the denominator can't equal 0. So we just write it as x such that x cannot equal 0, but all the other ones are fine. So x is an element of the real numbers. For the next one, absolute, no problems here. X is an element of the real numbers. And for this one, well, it can't exist over here to the left. So we must say that the domain is x such that x is greater or equal to the real numbers. Now, in this one, what they've done is they're asking us to look at these operations of functions and tell us which ones of these are actual functions. I just noticed there's a little bit of mistake right here. That should be in brackets. Well, let's look at this. F of x, well, f of x is that one right here, right? Let's put all that back. Okay, so the f of x is this one. That has no problems. G of x, where's g of x? Oh, that's the quadratic. These two both have no restrictions. Therefore, any operation of functions on those, addition or subtraction, will also not have any restrictions. H minus j of x. Well, h of x is the cubic, not a problem there. Now, j of x is going to give us a little bit of problem. We're not going to be able to find that because this is not, is undefined to the left of the zero. So while we're okay to the right of the zero, we have to restrict h minus j of x to the domain of that radical function, j of x. Now for k minus n of x, that one also seems to have dropped its brackets. We want to have k of x, no problems there, but m of x does. So when we combine it, this is going to be the restriction on this one right here. Let's keep going. Now this one, this is for you. I want you to write 2 or more combined functions that will have a limited domain using the 6 common functions, function notations, and the operation of addition and subtraction. So give it a try. Okay, let's move on. Let f of x equals x squared plus x and g of x equals x plus 3 and h of x equals x cubed. Determine the simplified equation for m of x equals f of g plus x minus h of x. Wow, that's a lot. So when we put it all together, we substitute the functions in. We could have, if we wanted to, added some little brackets right here. Not completely necessary, but we could have done that. And we combine our like terms. I like putting things in descending order, meaning starting with the highest exponent down to the lowest or constant. And then we combine the like terms to get this cubic function right here. Notice we get this nice little cube right here. Now it's asking us to graph m of x using technology. Well, I'm just going to put that in my calculator, reset my windows, and voila, I have m of x right there. If you would pause and see if you can recreate this, go ahead and see what you come up with. Now, notice here in the original equations, f of x is a quadratic, g of x is linear, and h of x is cubic. It's asking us, what function does m of x look the most like? The linear, the quadratic, or the cubic? And it's asking us, what do we think that is? Well, looking at the graph, we know that that looks like a cubic graph. And that kind of makes sense because, well, when we simplified that to the m of x, it retained or held on to the cubic term minus x cubed. So that played a major part in the way the graph looks. Now it's asking us to state the domain and range. Well, all of these things, cubics, quadratics, and linears, have no restrictions on the range or the domain, which means for the domain, x is the element of the real, and for the range, y is also the element of the real. So again, take some time, pause the video, and in the practice section, try some of these questions right here. 10, 11, 12, and the last one, 13. Well, that's the end of sums and difference. I realize it's a bit of a beast, hard one to get going on. But the next one, be a little bit quicker. If you have any questions about the video, any questions about the practice, make sure you get in touch with your teacher. I hope you have a great rest of your day. Take care.